Alright, I'm going to do a few problems about finding the volume of various solids using these graphs. This top one, by the way, is y equals 4 minus x squared, and this guy here is y equals 3 radical x. Now, this video is intended for people who pretty much have a grip on how to find volumes of solids of revolution and find volumes of shapes with known cross sections. So it's not, just so you know, it's not intended to be a full lesson on this from the beginning. But the first problem is find the volume or set up an integral. We're just going to be setting up integrals in this video. Find the volume of a solid that results when the region A is rotated about the x-axis. So it's a solid of revolution. We're taking this figure, spinning it about here. So if I could kind of try to draw this and get an idea of what it's going to look like, it's going to be something like this, something like that. So where the cross sections, right, if we take this figure, it comes up out of the page, it's going to be like, so each of our slices will be like this, right? And each one, if I could draw, maybe put some perspective in here, this will all get like a half a disc going, right? All the cross sections of which are going to be discs because of the way it's formed. So sort of see this piece as sticking out, being an exposed cross section, and the green line representing the one of the slices, the piece that's going into the page. So since the cross sections are discs, all we have to do is, it's basically going to be pi r squared. We just need to model the radius of our discs. We're going to be integrating with respect to x because we're slicing it this way. And the integral we'll get will be pi times integral. We're taking x values from, you find where this thing is 0, and that's at 2 and minus 2, so it'll be from minus 2 up to 0 of r squared, and the radius function is just going to be the function itself. So 4 minus x squared, quantity squared, dx. That'll be the first one. Number 2, find the volume of the solid that results when region B is rotated about the x-axis. So if I'm going to draw that in, that'll be like this, coming down, right, and mimic this up to here maybe, and then the rest will be like this. So it's this shape here, spinning it this way, and draw up a, you can see that if you take such a figure and you slice it this way, you slice it vertically, your cross sections will be washers. We got the hole in the middle. Right. Each of them will look like that, and if I put some perspective in here, it'll be like this. So there's an outside function and there's an inside function. And here's one typical piece. So the general formula for volume by washers is it's pi times the outer radius squared minus pi times the inner radius squared. And we usually collapse that into one integral. So that'll be, if we can see that down here, that'll be pi times integral. I'm probably going to run out of room here. The outer radius is from the axis up to the parabola, and that's 4 minus x squared. So that'll be 4 minus x squared squared, outer squared, minus the inner radius is just the other function. That's the 3 radical x. So that'll be the outside minus 3 radical x, quantity squared, dx for thickness. And the boundaries are from 0 to whatever this point of intersection is. If you set the two functions equal to each other, they intersect at 1, 3, so it'll be the x value is 1, so it's x varies from 0 to 1. Yeah, the x value is 1, not 3. Number 3, the third problem is find the volume of the solid that results when B is rotated about the line y equals 4. Right, so the axis is going to be a little bit different. We're rotating instead. not about the x-axis, but a different horizontal line, like so. So I'm going to try to draw this thing in here, and so it'll be like this, and there's this bulge right here. Try to match that up, and then the other side is taken up like this. So it's this weird looking shape, kind of a sort of a bowl shape, and make up a typical cross section. If we sliced it vertically, each of our cross sections would be washers once again. So we'll do this, and perspective. So each of them will look something like this. All right, we get wider ones towards the end. So once again, it's going to be volume by washers. So what we have to do again is model the inside and outside radii of these washers as a function of x. So I'm going to, let's see, I guess I'll use this. I'll try to squeeze it in here someplace. Maybe I'll just zoom in a little more so we can see. All right, we have to model the distances from the axis to the curve. So not from the x-axis up, but from this line, and the line, by the way, was y equals 4. From y, we need to measure these distances. I'll draw them in blue. All right. So the inside radius of each disk will be from the axis to the top curve, and the outside radius will be from the axis to, that's supposed to hit the bottom curve there. So we have to model these things as a function of x. Now we're going to use the function in that because we'll say that the whole distance between the x-axis and the axis of rotation is 4. So we want, when we plug x into these functions, we get the complementary distances of what we want, right? So we need, for example, since this one is the inside radius, it's going to be, the integral that I'm going to set up is going to be, if I can squeeze it down here, it'll be pi times the integral. We're still going to integrate from x equals 0 to x equals 1, so that'll be the same from 0 to 1. And the outer radius is this, so it's going to be 4 minus what this function is. Let me just kind of dash that in here in red. When we do the 4 minus x squared, that gives us this distance. But we're not interested in that distance. We want its complement that adds up to 4. So the inside radius is actually going to be 4 minus the quantity 4 minus x squared. The outer radius, which is what we want first, all right, we want this one first. So the outer radius is going to be 4, right, the whole distance 4, minus this function value, the 3 radical x. So the answer will be, the outer radius is 4 minus the quantity 3 radical x. That's for the outside radius, quantity squared, minus, and the inside radius is done in the same way. It's going to be, the whole thing is 4 less the distance to the top function. So that will be 4 minus, put the paren, 4 minus the function, 4 minus x squared, quantity squared, dx. So that's the answer for that one. Looks a little long. Number 4 says, find the volume of the solid that when C is rotated about the y-axis. So region C, instead we're going to spin it this way. And so let me try to copy that shape on the other side. I'll do it in black. So this region about here comes out of the page. We can ignore this and ignore the A curve. So it'll be something like, oh, it's got a similar shape to the other one, but instead it's spun about this vertical line. So since we know that if we cut it up horizontally, we make horizontal cuts, each of the cross sections will be annulus and annulus, right? Annuli. And so if I draw one in, a typical washer will look like this. It's going to be going up. And And so I'll put this on the inside there. So a typical half washer will look like this. This suggests that we're going to have to integrate with respect to y on this one. So take the functions and isolate y. And the first one, since the top function is 4 minus x squared, when you rearrange that, that actually will give you x equals, let's see, when you take it, the square root of 4 minus y, plus and minus. And the other one will be, it's y is 3 radical x, so you divide by 3, square both sides. So the other one will be x equals y squared over 9. That'll be the curve. And so we're integrating with respect to y. So we need the outer radius and the inner radius as a function of y. And I'll do it in blue again. Since here's the axis, the outer radius is from the y-axis out to this first curve here. Right? And the inner one is the axis to this one here. Luckily, we don't have to play any games with saying, not like in this one where we had to take it away from 4. Our radii are the values of the functions themselves. So I'll begin by just setting it up, and it'll be pi times. The integral, y is going to vary from, we're taking y values from the origin up to including this point here, which is 1, 3, I said. And so it'll be y varies from 0 to 3. And the outer radius is this distance, so it's the function that has the greater x coordinate, and that is the radical 4 minus y. So that outer one will be 4 minus y, radical 4 minus y quantity squared, outer squared, minus the inner radius is the other one, so that's y squared over 9, quantity squared. Right, outer squared minus inner squared, dy. Alright, just like that. 2 left. Alright, let's see, find the volume of the solid whose base is C, so we talk about this, and whose cross sections perpendicular to the x-axis are squares. Alright, so this C is the base of a solid, and if I could try to maybe draw this a little obliquely, alright, that would be if I draw the axis. The region C is a cross between 2 parabola-like. So let's say they meet at, I said 1, maybe 3. So that's going to look something like that if you kind of tilt it on its side, if this is the y-axis and this is the x-axis. And whose cross-section is perpendicular to the x-axis are squares. So anytime I make a cut going this way, the cross section is going to be a weird looking shape. It will be something like, will look like that. And if I take, maybe I'll take this large one here. That one is going to be huge. So this is a tough looking shape to imagine. But it's kind of like we got these smaller squares that sort of vanish at this point, and then they grow and they get real big, and there's a ridge over the whole thing. Following this ridge. There's one for the top vertices of the square, and there's another one for the other one, but I can't draw it in without making the whole thing look really weird. But the point is that any cross section will be a square, and so when we slide out each piece, all we need to do is find the area of the face of the square and multiply that by dx, and that'll give us what we want. For just a little bit more, let me just keep this in green here. This is the base of the curve. Yeah, base of the solid. Alright. With one cross section. So, this is not so bad. All we need to do is the bases of the squares will be these distances, right? Like 1. Now we're going to have to split this up because the distances from the axis to the top function, it's a different function starting at this point here. So we're going to have to integrate the one function from 0 to 1, and then the other one is going to take over. Right here's like our split point, and the other one is going to take over from 1 to 2. But since the cross sections are squares, it's going to be, come over, let's see, I'll do it up here. the integral, no pi on this because it's just squares. It's not a solid of revolution. Integral from 0 to 1. That's this region here. Since the lengths of the squares are the function values, and the heights are also the same. It's just going to be the function squared. So that'll be what is that? Radical integrate with respect to x again. 3 radical x quantity squared dx. All right, for the first one, and plus now we gotta do this one. The other one, I'll do that one in red. You got to split it up because the functions are different. Plus the integral from 1 to 2 of the other function, which is the 4 minus x squared quantity squared dx. That's that one. And finally, number 6 says, find the volume of the solid whose base is C again, but whose cross-section is perpendicular to the y-axis. So the cross-sections are going this way. Cross-sections perpendicular to the y-axis are semicircles. That's a little bit harder to, well, that's kind of hard to draw too, but let me see. I'll try to give an oblique version of what it could look like, just for a little bit of perspective. Alright, so we got this. Whoop. Like that, and we said again that they intersect at maybe 1, 2, 3. So that's about here. So it'll be up like this, and down like that. That's the base. Draw that out in green. And this, now the cross section is perpendicular to the y-axis, so we're slicing it the other way. We're slicing it this way. So this way. And it says these cross sections are semicircles. So you can see they're larger at this end, and they just get smaller and smaller and collapse to a point down here. The formula for the area of a semicircle whose diameter is f of x is pi over 8 f of x quantity squared, right? If this length is f of x, then pi over 8 f of x squared is going to be the face area. So, but we have to integrate this with respect to y. But all we need is the outer and inner function, the function with the larger x-coordinate and with the smaller x-coordinate. You can see any slice that we make, the left and right points that are important, intersect the same function, right? Like the right boundary is one function and left boundary is one function for the whole way through. So we don't have to split it like the last one. But you integrate with respect to y, and you look back the outer function with respect to y. If you take the outer function and isolate y, isolate x, just to remind us, that's radical 4 minus y, and this one is y squared over 9. So is going to be, since we're interested in the difference in these two, that's going to be the definite integral. Since it's y values, y varies from the y values that were taken are going to be from 0 to 3, and these lengths will be the function with the larger x coordinate, which is radical 4 minus y, so that's outer, minus y squared over 9. That's the inner, and we want to take those and square it, dy. Now that'll be, this right here gives us the volume as though the cross sections were squares, right? It's going to give us a larger answer. If we make these squares instead, they'll be much bigger. But no, it's semicircles, so we need to throw in a multiplier, and the multiplier for semicircles is pi over 8. So that's the answer for the final one. And there you go, 6 examples of setting up definite integrals for volumes of various solids. In case you just want the answers right away, here they are. The problems are in the description. The answer to number 1 is this. The answer to number 2 is this. The answer to number 3 is that. The answer to number 4 is this. Number 5 is these two. There's some. And 6 is this.